So, brief calculus. Up to this part of the class, we have been focusing on the derivative. And we have looked at many ways of using the derivative, which gives us the rate of change of a situation, how things are changing, that rate. From this point onward, we're going to be looking at something called the integral. And as we're going to go through this, we're going to see the derivative takes us sort of in one direction, sort of the forward direction. The integral is a way to undo the derivative to get us back to where we started, or to get us back to something we didn't know, but the integral undoes what the derivative does. And that's what we will spend the rest of the portion of the class doing. So much of what we're going to be doing is thinking backwards. So let's go ahead and get started and talk about this thing called the integral, and see how our knowledge of the derivative, of how to get a derivative, is actually going to be very helpful for us. We just have to think backwards, which for me is very easy. That's my normal mode, is thinking backwards. So the indefinite integral is where we're going to start. And what does the word indefinite mean? Simply that we don't have specific parameters. So we're looking for a sort of a general integral. Let's think of it in those terms. It's called an antiderivative or an indefinite integral. The word anti, though, has two different meanings. I thought of it in terms of anti meaning against, which is not really what it is. What it really is talking about is being the opposite. The opposite of something. Let me make sure I've got my pen here. There we go. So what we want to focus on is antiderivative, or underderivatives, as I like to think of them, as being the opposite of the derivative. So we're going in the opposite direction. We'll be doing the opposite methods of finding the underderivative, the integral. And what we're going to see we get is a family of functions. So here's an example just for motivation. I want you to think back to your algebra class, and the forward process we did in algebra, or one of the forward processes, was multiplication. So we oftentimes had problems where we were given a binomial and we were asked to multiply it, and many of us learned a system called FOIL, and we'll just go through that. We take the first two items and multiply them. That gave us x squared. Then we go with the outer two items, so the outside, this one and that one are the outside, so that gives us a negative 5x. Then we do the inner ones, so 3 times x, so there's a plus 3x here. And finally we do the last term, so 3 times negative 5, giving us a negative 15. We simplify, clean it up using algebra, adding like terms, or in this case subtracting like terms, x squared minus 2x minus 15. Okay. And when the question asks us to multiply, this was our final answer. So we boxed it in, and that would be it. A little bit later in the algebra class, we learned about something called factoring, which with factoring, we started where multiplication ended. And really the goal of factoring is to take the answer and work backwards to the question in this sort of way. So we would unfoil or reverse foil, as I like to think of it. And what we'd have to do is remember the process we went through when we were multiplying out. So we had to remember that this first term was the product of the first terms, the two first terms. So these terms here and here came from or when we multiply them together, that's how we got this x squared. So we look for factors of x squared, which are x and x. And we notice when it was something like 3x squared, those were harder problems to do. The last two terms here in these binomials, we had to remember, came or would result in this last number here. Remember this negative 15? And so we have to look at the factors of 15. Well, it could be 1 times 15, or it could be 3 times 5. But if we, as a process, we look here, well, there's a negative here. That means we're going to subtract them. 5 minus 3 is 2. That's the one we want to use because we've got a 2 in the middle. Had it been 14, then we would have used the 1 and the 15. Okay, so we went through these processes and we say, okay, we need a 5 here. We need a 3 here. And then we would work through it and we'd see, well, the answer is negative here, so we put a negative on the 5 because the 5 is bigger than 3, and we see we got back to where we started. That's very similar to the type of thing we're going to do with calculus. Okay, and one last thing is we could FOIL this back out, and oftentimes we did because sometimes we'd make mistakes with the signs here or the plus or the minus, but we would FOIL it back out until we got what we were looking for, and I'll just do a shorthand, and oh, it checks, yeah, okay, so this is the right factoring. Okay, and we use factoring for different types of problems than we use multiplication. So with that thought in mind, backwards and forwards processes, let's take a look at calculus. So differentiation is the forward process. Integration is the backwards process. So we're going to have a function, and this time we'll use capital F just to be consistent with the way the text talks about this process of integration. And then with differentiation, we're given a function, and then we're asked to find that function's derivative. And again, just the notation, the derivative of capital F, we'll write it as little f. A little different than what we did before, but it's what sort of the text uses from now on. And remember the process is we would take this 2, bring it down in front. That was multiplication. So take the exponent down and multiply. And then you subtracted 1 from the exponent. 2 minus 1 is 1. So that's 2x to the 1 power if you want. Remember this one, the next term, we did term by term. So the exponent comes down. So 1 times negative 3 is negative 3. Subtract 1 from the exponent. 1 minus 1 is 0. X to the 0 power is 1. The x is gone because it's just 1. And then we remember that when we take derivatives of constants, we get 0. So we have a plus 0, which we don't write down. So this is our derivative. Okay. So with integration, as you notice, just like we did in algebra with multiplying and factoring, we're starting with what was the answer to the differentiation process. What we really need to do is work backwards to get back to the original function. So we want to find that original function that we started with before we took the derivative. That's what integration is. We'll go through the full process in a little bit, but just to think about it, what did we do over here? We took the exponent down and multiplied, and then we subtracted 1 for the exponent, right? So we did, we took the exponent and multiplied. Second step, we subtracted 1 from the exponent. So over here, we're going to do the opposite and in the reverse order. So what we're going to start with is we're going to add 1. First step. We're going to add 1 to the exponent. And then, instead of multiplying, we are going to divide by that new exponent. So you see it's very similar to what we've been doing, and hopefully you'll catch on, but it is backwards. It's a backwards process. So what's the exponent here? It's 1, so we're going to add 1. 1 plus 1 is going to give us 2. So that's x squared. And we've got a 2x squared, so that's what we've got so far. And then we divide by that new exponent. The new exponent is 2. We do the same thing with the 3, and let's think of this as 3x to the 0. Remember, that's really what it was. We're going to add 1 to the exponent, so that's going to be x to the first power, and then we're going to divide by that new exponent. So it's going to be minus 3x to the first power divided by 1. Now there's no constant term here, but remember, when we take a derivative of a constant, we get a 0, so there could be a constant here. In fact, we know there is. We know it's supposed to be 5, but in this particular problem, we haven't been told that. So what we do is we say plus something, some constant. We'll put a c there. So we do the simplification now. 2 divided by 2 is 1, so we get x squared minus 3x plus the constant. Okay. Notice we have very close to what we started with. We just don't know this 5 is a 5 unless we have some extra information to work with, which is what we're going to, you'll see we'll be given some initial value or some values where we'll actually be able to find out that 5 for a particular case. But this is the quick review. What we're going to do now is go through sort of step by step and take a look at the textbook's process, get comfortable with the notation and the wording, and but you'll see this is basically what we're doing, except in the cases of exponentials and logarithms, and we'll talk about those, but again, backwards process. Here we are. So again, to get the antiderivative, the underderivative if you want, it's they use the little f is that antiderivative. It's a function of big F. Okay, so you'll just have to kind of get used to this. We'll use the capital F. When we take its derivative, we get the derivative little f. So from now on, when you see little f, that's going to be primarily referring to a derivative, but we'll see if they keep the consistency. So an example, 4x to the third, is the antiderivative of x to the fourth. And why is that? Well, if you take x to the fourth and you take its derivative, the 4 comes down, you subtract 1 from the exponent, and that's what you get. So oh, sorry, I read it backwards. 4x to the third is the antiderivative is x to the fourth. Okay, so x to the fourth is what we start with. The derivative is 4x to the third. Okay, so this is where it kind of gets a little confusing. It just says basically if the derivative of a of x is b of x, so b is the derivative, then the antiderivative of bx is a of x. So these things travels in pairs, just like with multiplication and factoring. One does it, the other undoes it. So they are related in that sense. So we can call the set of all antiderivatives of a function the indefinite integral. So again, that's going to have a plus c on the end once we get done with it, just like up here when we integrate. So we've got this derivative here. When we integrate it, and we're going to see this symbol will be this little sort of s, what we do is we get x to the fourth plus some constant. Okay, so an indefinite integral, again, what we're doing is we're integrating some function that we could view as it is a derivative. What we want to do is we want to get back to the function we had before we took that derivative. Yeah, why did we spend all this time taking derivatives if we want to get back? We just, that's the way it works. So we read this as the indefinite integral. So notice Eventually we'll have some boundaries on this, but right now there's no boundaries, so it's an indefinite integral with respect to x. And it's the set of all antiderivatives of f, because once we get done, we're going to see that this will be equal to some antiderivative function. And it's a whole family of them, because there's the potential of this constant that we don't know what it is. And this constant could really be anything. It could be 0, it could be 27. So the function f that is being integrated is called the integrand. Again, just some vocabulary. We won't test you specifically on it, but what is the integrand? It's the thing inside the integral. X is the variable of integration. Okay. So the quick example we did, 4x to the third is an integrand. When you integrate it, you get back to the function x to the fourth plus a constant. Okay, kind of like we talked about there. So that's the family, because c could be many different things, could be an infinitely many things. So every possible antiderivative has this form. The constant of integration c is what we call it. Reminds us that we could have any kind of a constant there. Because remember, when you take a derivative of a constant, you end up with 0. Evidence is destroyed. We have no way of figuring it out unless we have a few clues, which we will see towards the end. We will do that. Okay. So how do we calculate indefinite integrals? We've already done one example, and it really is I don't know if you remember at the beginning of this course, I told you if you know how to subtract and add 1, you're going to be just fine, because that's really what we've done. For the most part, what we've been doing is subtracting 1 to find the derivative. So now we're going to be adding 1 to that exponent to find the antiderivative. Okay. So here's some review from 11.1. This is where we first started talking about our derivative rules. I changed it a little bit from the slide that you saw because we didn't use capital F, but to be consistent now, we're going to use the capital F. If this is our function x squared, when we take its derivative, it becomes, remember the exponent comes down in front, that's where the 2 came from. Subtract 1 from the exponent, so it's now 2x to the first power. Just remember what's happening there. When it's x to the third, it's a little more clear. The 3 comes down in front, there it is. And then we subtract 1 from the exponent. 3 minus 1 is 2. That's all we're going to be doing, okay, with finding the derivative. What we're doing now is we're going to start with the derivative and go backwards, okay? So again, what we talked about is the first power rule we dealt with when we were taking derivatives is the exponent first comes down, and then you subtract 1 from it, okay? So how do we undo this? Again, first step was multiply, that's not an x, it's a multiply, by the exponent. And then the second step was to subtract 1 from the exponent. So to undo this, we're going to do the opposite. We are going to first add 1, and then second, we're going to divide instead of multiply by the new exponent. Okay. So here's our power rule. And then we're going to see there's a special case when n is -1, because if you had if -1 and you add 1 to it, you get 0, and that's going to not quite be right. So anytime we're integrating something to a power, we simply add 1 to that exponent and then divide by that new exponent. That's all there is to it. Of course, we're going to get into versions of the product rule and the chain rule and the quotient rule. When you do integration, those can get a little bit tricky. But at the starting point, it really is just as simple as adding 1 to the exponent and then dividing by that new one. Now, the special case when x equals, or when the exponent is -1, well, remember when you had the natural log of x and you took its derivative, we ended up with 1 over x, which is x to the minus 1, right? Which is the same thing, and we're going to see another version. Okay, so that's when we integrate this, we need to get back to natural log of x. That's just one you're going to have to remember. And here's the case. So you'll either see it as x to the minus 1 or 1 over x. But when you integrate that, that one is natural log of x. Just have to remember that one. So every other one, you add 1, and you go forward. This one's not too hard to remember because when you add 1, you get 0, and it just seems real weird, and it is. It's the one that where you need the natural log. Okay, so here's an example. X to the 55, just add 1 to it, so you get x to the 56 power, and then you divide by that new exponent, divided by 56. Because this works, because if you were to take this derivative, x to the 56 divided by 56, let's take its derivative, right? The 56 comes down in front, and we're multiplying. And then you subtract 1 from the exponent. 56 minus 1 is 55. The 56 cancels with the 56, and we're right back to that x to the 55 power. So notice how we got right back to the derivative. Okay. Again, the constant, you take its derivative, it's going to be 0. So this is the other case, is when we have e to the x. Now remember, e to the x is its own derivative, as shown right here. So when we take the derivative of e to the x, we get e to the x. So when we integrate e to the x, we get e to the x. The only thing that you can tell the difference of is that we also get this constant. Because if you take the derivative of a constant, it's 0 and it disappears. So just always remember that plus c. Okay. Now, if we had, that's only with the fact of e, the base is e. If we have the base as being some other number other than 1, of course, because 1 is not an exponential, then what we get is we get that base to the x, remember, because that's basically its own derivative. But this time we're going to divide by the natural log of b, because... Why? Because when we take the derivative, if you were to take the derivative of b to the x, you get b to the x times the natural log of b. Okay, and so we need that to cancel out some way, so that's why we divide by the natural log of b, right? Because these guys will cancel out and you just get b to the x. So you just have to remember it comes from understanding what the derivative is, and we're going to go backwards. Let's not even worry about this. There's no problems that we're going to be working with absolute values. So we'll skip over that. If you have an interest, bring it up during office hours, and you know, we can talk about it, but you don't need to worry about it. But you could kind of see here, if we take its derivative, we do get absolute value of x. Okay. Good. So an example, you got 2 to the x. What is it going to be? Well, the antiderivative would be 2 to the x divided by this. And how do we check? Well, you could check by taking its derivative. Derivative of 2 to the x is 2 to the x times natural log of 2. And then this natural log of 2 that's under here is still there. Derivative of c is 0. These cancel, and what is left is just 2 to the x. We're back to, that's what we started with. So this is the integral. Okay, now this one, it looks more complicated than it is. It's just saying if we've got a sum or difference. So in this case, if we had x squared plus x, And in this case, f of x would be x squared, g of x would be x. So you can separate them, take the derivatives, the integrals separately, just like we did with derivatives. So we would integrate x squared, which is, again, add 1 to the exponent, so that becomes x to the third, and then divide by that new one. This one is x to the first, so what we do is add 1, so this becomes x squared, divided by 2, and since we started off with a plus, our answer is a plus, and we'll have a plus constant. We'll look at a few more examples, but that's all this is saying, is looking at them as sort of separate functions unto themselves. So x squared plus x, you could look at it as one function, or you could look at it as two functions being added together. So it just makes it easier to talk about taking the integral. So the integral of a sum is the sum of the integrals. That always got my mind spinning. Just do it one term at a time. Okay. If we have some constant multiplier, some number like 5, you could take it outside. You don't really have to do anything with it. It's still going to multiply by your final answer. K is some kind of constant. Some number like 5, 10, 15, 20, 78 million. Let's back up here. I went too fast. So here's a sum rule again. This function would be x to the third, and then g of x would be 1. So you break it up into two pieces. And again, remember, whenever you have just a constant number, you can think of that in this case as the integral of 1 x to the 0. So you have something to work with. Add 1 to the exponent, right? Add 1, and then divide by 1. So you're going to get x to the first power. Here we go from x to the third, add 1, you've got x to the fourth. But again, divided by the 4, because when you take the derivative, the 4 would come down, so we need it to cancel out. Okay, so again, they've shown the two functions how they're looking at it. Constant multiplier, again, why did I come up with 5? I must have looked at this. So you can basically, the 5 is a constant, it's multiplying, just take it outside and let it work. Tag along for the ride. Figure out the integral, x to the fourth over 4, and then multiply it by 5. Okay, so that's how you apply that one. Going to look at a few applications. In the homework, at least this time, you'll see two application type problems at the end that are very similar to these, so we will go over those. If you wanted to, most of the homework, you are ready to go ahead and start doing it. You might want to go ahead and start in, get some practice with it. Come back to this part of the video later if you want, or keep looking. It's, again, understand what your learning style is, what works best for you. And I don't know, maybe I should break these up smaller, but either way I do it, it works out. So some applications. Okay, here we have, we're given a marginal cost. The marginal cost to produce some baseball caps. Now remember, a marginal cost, that's a derivative. So we're given the function, the marginal cost function, which is a derivative. It's a derivative of the cost function. So if we want to find the cost function, we now have that ability because we can integrate this. If we take the derivative and we integrate it, and again, we'll treat this as two separate ones as we work through there, we will get the cost function. Again, it'll be plus a constant, but you'll see we'll come back to this piece of information here. 100 caps is 500, and we'll actually be able to find that constant. So for the solution, to find c of x, we need to find the integral of the marginal cost function. Why is that? Because the marginal cost function is a derivative. So to find c of x, we do what we say, we find that integral. Okay, and again, the process here is we want to think of it as 4x to the 0 power. We're going to add 1 to the exponent, and then we're going to divide by that new exponent, which is 1. So we're going to end up with 4x to the first power. This one over here, this term, again, treat them term by term. It's x to the 1 power. We add 1 to it, so that's going to be x squared. And then that means we're going to have to divide by that new exponent. Okay, so we're going to get minus 0.001 divided by 2 is going to be 0.0005 x squared. So that's, you're going to see, and they'll take us through a few of these steps. K is, I forgot, yeah, plus K, plus C. But see, since we're using C for the name of the function, we can just get creative and let's call it K for constant. So we get there, and again, if you take this 0.001 and divide it by 2 in the next step, they give us the full value. So that is our function. Again, it's a family of function. We don't know what that constant, the K, is. It could be many different numbers. It could be an infinite number of numbers. So there's a lot of solutions. But what we're going to do is we are going to take that piece of information that when we plug in 100 for x, the output is going to be 500. Okay, so we're going to come up and use this. We're going to put 100 in for the x's, and it's going to be equal to 500. So they'll do that for us here, plugging in the 100, and then the C100 becomes 500, right? Because we know that the statement was over there. C of 100 equals 500. It's a substitution there. They do the math here and get 395. Subtract 395 from both sides, you get that K equals 105. And so we get the full cost function right here, replacing K with 105. Okay. So now we have this ability, if we know the derivative, we can get back to the original function. And remember, the derivative is the rate. So oftentimes we do have data that gives us a rate of change, and we're able to come up with that function. And if we can come up with the rate of change function, we can get back to the original one, where we might not have the tools to directly get this, in this case, a cost function. A very powerful tool. And here, okay, motion in a straight line. And so this is, well, let's just go for it. This is a reminder back from 12.3. We talked about second derivative. So we've got the function that gives us location or position of a particle, of a person, of a car. Let's call it a car, it's more interesting. And then when you take the derivative, the rate of change of a car in motion is its velocity, its speed. Velocity is directed speed, so you'll see we're going to use plus and minus depending upon whether we're going up or down or left or right or something. And then when we take the derivative, the rate of the rate is the velocity, the acceleration, how fast it is. So, if you're picking up speed very quickly, that's when you get the whiplash, okay? Or if you're stopping very quickly, that's a change of velocity very quickly, you get the other reaction that way. That's acceleration. That's what we feel. It is not just speed that's so much fun, it's that acceleration that really gets those thrill speakers. And I've got a video here at the end. It's not about, you don't have to watch it, but some of you might find it interesting anyway. Okay, so it's this relationship between these three functions. Position, take its derivative, you get velocity. Take the derivative of velocity, you get acceleration. And again, we used it to think about taking two derivatives of the position function, we could get to the acceleration. Well, now guess what we can do? If we know acceleration, we can get to velocity. If we know velocity, since velocity is the derivative of position, we can get back to position. Since acceleration is the derivative of velocity, if we know acceleration, we can get back to velocity. So this is what it allows us to do. Take the integral of velocity, we get back to our position function. Great. take our acceleration again, and that's something that could maybe be measured, how much our back of our head hits the window of the pickup truck as we speed off. We might be able to measure that. That would allow us to get the velocity. How fast are we going? Okay, so multiple ways to get through there. And so we'll look at some examples here. Give us an example. If we know the velocity is a function that's 4t plus 1, we integrate velocity, we integrate 4t plus 1, and we know that the position function then is going to be 2t squared plus t plus c. And again, we'll go through a few of these examples, but notice this was t to the first power. Add 1 to it, you get, that's how it's squared. Divide by 2, 4 divided by 2 is 2. That's all that happened. Remember, this is x, this is 1x to the 0 power. Add 1 to it. Oh, not x, we're using t, sorry. I like to use x all the time, then I don't ever make these problems. T to the 0 power, add 1, you get t to the first power, right? And then divide by 1, you get the invisible 1 in front. And then always remember we've got a plus a constant. Just a quick example. So now we're going to take that quick example, and same thing, we've already really calculated that, but what we're going to be able to do is this gives us sort of some data, some information about the position. We're told that s equals 2 meters at time t equals 1. So what does that mean? It means that s of 1 equals 2. So we're going to work with that integral. Okay, so the quick example, position function is the integral of velocity. There's a velocity function, and just as we talked through it, it integrates to 2t squared plus t, and we talked about that. Now what we're going to do is use the fact that s, right, s is 2 and t is 1. So just like we wrote up there, s of 1 equals 2. So take that function, plug in 1 everywhere there's a t, and the whole thing is going to be equal to 2, so you're able to solve for c, do all the algebra. This one over here gives you 2 plus 1, that's 3. Subtract 3 from 2, you get negative 1. That's what our constant is. So then it gives us the full mill deal. 2t squared plus t minus 1 meters for that position function. So you see, having the rate of change, the derivative, allows us to get back to the original function, and then having a little bit of data. When x is this, y is that, we're able to actually come up with that constant. So that's kind of the theme that we'll play through in this section. We'll move forward, and this is basically it, the same concepts, but there'll be a few more interesting things added, but we'll keep moving forward. Okay, so with this one, think about this is the acceleration, the velocity acceleration due to gravity. So a freely falling body experiences no air resistance and 0 initial velocity. So like a bowling ball. Find an expression for the velocity v in terms of t. So on Earth, a freely falling body experiencing no air resistance accelerates. So they've measured this, that the acceleration is constant everywhere due to gravity. It's got an acceleration of 9.8 meters per second. Again, that's using metric. In the system we might know it's 32 feet per second. So you physics majors, there's no physics majors, you're all business majors, right? But that's where the physics comes in. Okay, so watch how this works. We know the acceleration is minus 9.8, and again, because we're falling, we're going to look at that acceleration as negative because its direction is coming down. If it were going up, it would be positive. That's what that explains there. So we're going to get to velocity, we're going to, which is speed, is what we think of, we're going to need to integrate this, integrate the acceleration, find the antiderivative, and so we take negative negative 9.8. Now remember, that is negative 9.8 t to the 0 power, right? Because this is 1. We're going to add 1 to the exponent. That's why we're going to get t to the first power. We're going to divide by 1, and you keep seeing me do this, and you say, why does he do that? When you divide by 1, you get nothing. I want you to remember to always divide by that, by the exponent, the new exponent, okay? And so you're going to see we end up with negative 9.8t plus some constant, okay? Can we find out that constant? Of course we can, because we were told that at the beginning time, there was no velocity, or the velocity was 0. It wasn't moving, so it was just dropped. Okay, so since we know that 0, 0, we take our function, we plug in 0 for t, the answer is 0, and so we find in this case c is equal to 0. So simply our velocity is going to be negative 9.8 t. So starting with nothing, no air resistance, and that gives us, from having acceleration, we get velocity. Could we get to position function? Of course we could. We take the integral of the velocity. We don't have to do it for this one, but so what we find though is velocity gives us this basic function, negative 32t plus the initial velocity. In that case it was 0, so it started at 0. If you integrate this, notice this is to the first power. Where are we? I'm over here. This is to the first power. So if you add 1 to it, you get t squared. And then when you divide by 2, 32 divided by 2 is 16. So that gives us our position function. And again, this initial, when you integrate this is t to the 0 power. Add 1 to it, you get t to the first power. And then, of course, you get another constant, which is whatever the beginning position was. So if you're going from a plane or something, and you're dropped, this would be the starting point. Okay, and this is the same deal in metric. So you could walk through that again. 9.8 divided by 2 is 4.9. That's where that came from. Okay, initial velocity, initial position, and we can use it. So with these, because these problems are used so often, things are always falling because of gravity, right? So that's what controls motion for the most part. Talk about one other thing, and so if I know some information simply about, like, a ball is thrown, it's got a velocity, initial velocity of 2 feet per second, and it starts at a height of 200 feet. I'm on a hill or something and I throw it down, or I'm on a building and I throw it down. What I do know about the velocity is that it's going to be minus 32t, which is 32 feet per second. And then also this initial velocity, it had a starting of this. So this would give me my velocity. And simply because that's the basic function, right? There's a minus 32t, there's the initial velocity. It was 2 feet per second. I can use that same one to come up with the formula here for the position function. Again, this came from integrating the velocity function. But I could also just memorize this or look it up, and there's the 16t squared. So when you're looking at gravity functions, you'll see this minus 16 x squared t squared all the time. The initial velocity is right here. There's the minus 2 because it's down 2 feet per second. Had it been thrown up 2 feet per second, then it would be a plus 2t. And then it's starting at 200 feet. There it is, 200 feet. Okay, so that's how we do it. Now, at this point, this gives you enough to get all the way through the homework. So, but I just had one thing, all of this is based upon no air resistance. And what I wanted to think about is there's another, and again, this is totally, if you're interested, go ahead, and if you're not, I'm not, go ahead and take off. Okay, you can stop here. But if you're interested, there's something called terminal velocity. And because there is air resistance, at least in our atmosphere, right? If you're in space, it's different, but here we've got air resistance. So terminal velocity is simply the maximum velocity you can obtain, that an object can obtain. And it's different for the objects because it depends on the resistance from the air. So, humans falling. if you're in this position, this is the most stable, you're still the maximum. This is good news, I guess. You won't get faster than 120 miles per hour. That's your terminal velocity in this position. So if you ever watch those movies where somebody's chute doesn't open and then someone dives down, is that really possible? Well, yes. If you go into the head down free fall position, you can get up to 180 miles per hour. That's a 60 mile per hour difference faster than the person whose chute won't open. You could catch up with the person and then pull the chute, save somebody's life that way. But here's the really cool part for you, really adventurous ones. If you do further streamlining and equipment and stuff, you can actually get up to 310 miles per hour. The 120 is too fast for me anyway. So what I like is this one, is that by using a parachute, you can get down to 12 miles per hour. That's about as fast as I want to be going. Even that's gonna, I think, would hurt a little bit when you hit the ground at 12 miles per hour. But that's what the chute is for. Is it reduces that terminal velocity way down. Instead of going at 120 miles when you hit the ground, you're only going 12, and that's good. Again, you're welcome to head out at this point, but I thought it was kind of interesting. There's this little video. It's about 12 minutes, 45 seconds long. As I was looking at this, got on this idea of terminal velocity. And again, this is way off track. So if all you're concerned about is the business calculus, you're probably already left. But here's a video you could take a look at. I'm going to show you just a little bit, but it was kind of interesting. I ended up watching the whole thing too. Guy skydiving from a balloon to see how fast he could get. And here it is. Let's see if I can get it to run. Oh, here we go. Well, I can't get it to run. Anyway, it was really cool. He gets up to like 350 kilometers per hour or something, the fastest guy. The video is stored. Go to the link. It's on YouTube. It's also in the PowerPoint. I downloaded it into there. So you can take a look at that way if you want to look at it. But just interesting things that you can do with calculus, right? So keep up the good progress. We'll move on. The rest of this class is going to be focused on integrating.